Welcome to a lesson in proportionality and the constant rate of change. In previous lessons, we've talked about the meaning of proportionality, constant rate of change, and quantity. So if two quantities are proportional to each other, then if you scale one quantity by some factor, you must scale the other quantity by the same factor. That's called scaling. One quantity is always sometimes large as another. That's the constant multiple perspective. The ratio of two quantities is always constant. This is the constant ratio perspective. We also talked about constant rate of change. And two quantities are related by a constant rate of change if the change in the quantities are proportional. Lastly, we talked about quantity. And a quantity is an attribute of an object or a situation that we can imagine measuring. Let's look at an example. A tank is being filled with water. For this situation, we'll investigate the height of the water in a tank and the amount of time that is elapsed. We also have some measurements that were taken as the tank was filling with water. We measured the time that it was elapsed in minutes, and we also measured the height of water in the tank, measured in centimeters. So here are some measurements, and what we're going to do now is to determine some answers to some questions. The first question is we're going to demonstrate that the quantities are not proportional to one another. And then we're going to also demonstrate that the quantities are related by a constant rate of change. That is, that the changes in the quantities are proportional. So let's begin with that first question. To demonstrate that the quantities are not proportional to each other, we have three perspectives of proportionality we could choose from. I'm going to pick the constant ratio perspective to highlight that they are not proportional to one another. So to do this, I'm going to take the ratio of the output, which is the height of the water in a tank in centimeters, and I'm going to compare it to the input, which is a time elapsed in minutes by division. So I'm going to take 13.06 divided by 1.8, that gives me 7.26. I take 15.65 divided by 2.5, that gives me 6.26. I take 20.83 divided by 3.9, that gives me 5.34. And I take 33.78 divided by 7.4, it's equal to 4.56. Now realistically, after I got the 6.26, I already had known that the ratio is not constant, because for quantities to be proportional to each other, all four of these ratios should have been the same, and they're not. But what we have done is we have demonstrated that the quantities are not proportional to one another. Now let's look at another one, which is we want to demonstrate that the quantities are related by a constant rate of change. That is, that the changes in quantities are proportional. To do this, we're going to need to make a table, and we need to record those changes between the input values and also the output values. So what we want to do is to figure out what is the change to go from 1.8 minutes to 2.5 minutes. And that is 0.7 minutes. Then we do the same, 2.5 minutes to 3.9 minutes. That's a change of 1.4 minutes. 3.9 minutes to 7.4 minutes. That is a change of 3.5 minutes. And then we're going to follow a similar process to figure out the change of the height of water in the tank in centimeters. So a change of 13.06 centimeters to 15.65 centimeters. That would be a change of 2.59 centimeters. And to go from 15.65 to 20.83, that's a change of 5.18. And to change from 20.83 to 33.78, that is a change of 12.9 centimeters. Now, to figure out any of these from earlier examples and earlier videos, we could just simply take the ending value minus the starting value to get one of any of these values. So for example, if I took 20.83 and I subtracted 15.65, that gives me 5.18. What we're going to do now is just focus on those changes. So to do that, let's bring this part of the table a little bit closer to just simply focus on what's happening with the changes. And what we're going to do is to see if the changes in the quantities are proportional. So the first question, do these quantities have a common scale factor? So for example, if I'm trying to figure out the scale factor from 0.7 to 1.4, that's the multiplication of 2. So the corresponding output should be also working by the same scale factor. So if I take 2.59 times 2, I do get 5.18. Now I'm going to look at the next one. If I take 1.4, what is the scale factor that takes me to 3.5? Well, that is a scale factor of 2.5. So the corresponding outputs should also be related by the same common scale factor. So if I take 5.18 and I multiply it by 2.5, I do get 12.95. So the answer is yes, these quantities do have a common scale factor. Now let's look at, are they related by a constant ratio? So to do that, I'm going to take the output and divide it by the input. So for example, 2.59 divided by 0.7 gives me 3.7. And my expectation is that they should all be 3.7. Let's find out. 5.18 divided by 1.4 is 3.7, yes. And 12.95 divided by 3.5 is 3.7. So yes, they are related by a common ratio. These quantities are related by a common ratio. So, to take away any change in height divided by a change in time in this context will result of a constant ratio of 3.7. Okay, let's look at one more way. Are these quantities related by a common multiple? So let's see. If you take 0.7 and multiply it by 3.7, you get 2.59. That's correct. If I take 1.4 and times it by 3.7, I do get 5.18. And if I take 3.5 times 3.7, I get 12.95. So the answer is yes, these quantities are related by a common multiple. If I take any change in time and I multiply it by 3.7, in this situation, I will get the corresponding change in height. So an easier way to write that, or another way to write that, is the change in height is equal to 3.7 times the change in time. So let's take a look and see what this means. Because the change in time and the change in height are related by a constant rate of change, we've just shown that, we can say the following. If we scale the change in time by some factor, we must scale the change in the height of water by the same factor. That's the idea of scaling. The ratio of the change in the height of water to the change in time elapsed will always be constant. And that is the ratio of the change in height to the change in time will always be 3.7. It's the constant ratio perspective. And the change in the amount of water will always be 3 times the change in time elapsed. And that's the delta H is equal to 3.7 times delta T. And that's using that constant multiple perspective. So what this means is now that because delta T and delta H are related by a constant rate of change, we can say the following. We can say that 3.7 centimeters per minute is our constant rate of change of the height of water with respect to time. In particular, note that the units of the constant rate of change, which are in centimeters per minute, are expressed in the form output units per input unit. So looking back at our original units, the height of the water in the tank was measured in centimeters, so that was the output quantity was measured in centimeters. The input quantity, which was the time elapsed, was measured in minutes. So that is why we have the units of the constant rate of change as centimeters per minute. So let's take a summary of this constant rate of change. In general, if two quantities are related by a constant rate of change of output with respect to input, we can determine the value of that rate by using the ratio of the change. That is, that the constant rate of change is the change in output over the change in input. So 3.7 centimeters per minute was the constant rate of change of the height of water with respect to time in the previous example. Now, some quantities might not be proportional to each other. However, they may be related by a constant rate of change. In this example, the quantities were not proportional, but they were related by a constant rate of change. So now let's take a little look ahead of how constant rate of change has some very interesting properties and why it's useful. So if we were to take and make a plot of the values that we see in the table, you'll notice that if we were to pass, that it would appear that we could fit a straight line through it. And when you actually draw the straight line, a straight line goes through all the points that are related by a constant rate of change. So that's a special property of quantities that are related by a constant rate of change. Let's look at another situation that is also related by constant rate of change. Suppose there's another tank that is being filled by water. And the dot over here represents a situation where when you have 2.25 minutes, the height of the water is 10 centimeters. Now, for every 2 minutes that go by, for a change of 2 minutes, the height of the water in the tank goes up by 9 centimeters. So that's the change in height. And when it happens is when we look at the constant rate of change, based on the fact that the quantities are proportional, using that scaling perspective, if we take half the change in time, correspondingly it's half the change in height. And we'll put a dot there as well. And if you take 3 times the change of the original time, that corresponds to 3 times the change of the original height. And you can see that for each of these so here's a first change in time, a first change in height. Here's a second change in time, a second change in height, and a third change in time, and a third change of height. When you look at all these values, you'll notice that if you were to draw a line through those particular points for which the quantities occur, you notice that a straight line goes right through it. So again, looking ahead, that is a special property, and what we say is that quantities that are related by a constant rate of change are linear. And so two quantities that are related by a constant rate of change if the changes in quantities are proportional. And when they are related by a constant rate of change, that context will be linear. And what that means is that a straight line can be drawn through all the plotted points in the graph associated with that context. So that's a look ahead of how constant rate of change is very useful. I hope you found this helpful.